In the last class, we looked at the concept of work done and kinetic energy. Today, we will see what is called as the work energy theorem and the concept of potential energy, and which leads to what we call as the principle of conservation of mechanical energy, and times when this principle is valid, times when we have to be careful when we use this principle. So, let us start. So, we start with first what we call as the work energy theorem. We have seen the concept of kinetic energy, and at any point if a particle of mass m is moving with a speed v, the kinetic energy of that particle is given by half m v square. Now, if a particle moves from position 1 to position 2 such that at position 1 its speed is V I, and at position 2 the speed is V f, then what we can see is the kinetic energy at position 1 will be equal to half m V I square. The kinetic energy at position 2 is equal to half m V f square, and the change in kinetic energy we can write it as half m V f square minus half m V I square. This symbol delta which we use, this means change in, and this is always the final state quantity which we refer to minus the initial state. And the work kinetic energy theorem or the work energy theorem tells us that the work done by forces when the particle moves from state 1 to state 2 is equal to the change in kinetic energy, and this is simply the work energy theorem. W is the work done by external forces acting on the particle as it moves from state 1 to state 2 or from state I to state F. So, the work done by external forces is equal to the change in kinetic energy, and this work done by external forces will be the work done by net external forces or sum of external forces which are acting on the particle. So, this is external forces represent the net external forces, or we can write them as sum of all the individual external forces which are acting on the particle. So, we calculate the work done by each of them, add up all these work done, and this work done must be equal to the change in kinetic energy. And we can very easily show this by two methods. Let us start with the definition of kinetic energy. Kinetic energy is equal to half m v square. We differentiate this expression with respect to time. So, we get dk by dt is equal to half m, mass being constant, times derivative of v square. So, this will be equal to half m 2 v dv by dt. Note here v is the speed, and so this we can write it as m times dV by dt times V, and this m times dV by dt, this is nothing but the force acting on the body. So, this will be equal to F times V, and this is equal to dk by dt, and V we can write as dx by dt, where x is the direction of motion. So, therefore, what we get is dk by dt is equal to F times dx by dt, and if we use the notation that dk by dt is delta k by delta t in the limit delta t goes to 0, and dx by dt is equal to delta x by delta t limit delta t going to 0, then delta t on both sides can go away, and this will give us dk is equal to f dx, and if we integrate this, then we get integral from state I to state f of dk will be equal to integral from f dx from xi to xf, and this integral dk from I to f will be nothing but change in kinetic energy, and integral f dx from xi to xf is nothing but the work done by the force F. So, therefore, what we get is we start basically, if you see, to get this expression, we have used Newton's second law, we have used F is equal to ma. We have used the expression F is equal to ma. This derivation which has been done was for a one dimensional formulation, which means that force is along this one direction, let us say x, and the movement of the particle is also along x. Well, this derivation has been done for a one dimensional motion, but this is also valid for a general case, and if it is a general three dimensional motion, for a general case also the work energy theorem is valid, and by general I mean 2D or 3D motion, and here what we will use is, if we have a general case, then we will have to use k is equal to half m v dot v. Now, we use the velocity vector and we write the kinetic energy in this form, and now when we use dk by dt, we will get this as half m times 2 times v dotted with dv by dt, and then this 2 and this 2 will go away, m can be taken with this. So, this will become equal to v dotted with m dv by dt, and m dv by dt will be nothing but f, and what we will get is dk by dt is equal to f dotted with v, and for a particle v can be written as dr by dt, where r is the displacement vector for the particle. So, this becomes equal to f dotted with dr by dt, and from here what we get is dk is equal to f dotted with dr, and when we integrate this, we get the same formulation for the kinetic energy, even for a three dimensional case. So, this is the work kinetic energy theorem. Now, we also see that this is basically work kinetic energy theorem is an integrated form of Newton's second law. And this we can also see if we look at simple one dimensional motion, if we look at F is equal to m times dv by dt, m times acceleration, this is Newton's second law, and this we can write it as m times dv by dx into dx by dt using the chain rule. And now, here what we have then is this dx by dt, we can write it as m dV by dx times V, and then we take the dx on the other side. So, we will get f dx, we take dx on the left hand side. So, we get f dx is equal to m times V dV, and when we integrate this we get the same thing, because then V dV when we integrate this will become equal to m times V square by 2 from state I to state F. So, this becomes the change in kinetic energy, and the integral of F with respect to x will give us the work done. So, therefore, the work energy theorem is an integrated form of Newton's second law. Now, because we are using Newton's second law, so therefore, this is valid only if acceleration, velocity, displacements are being measured with respect to an inertial frame of reference. So, for the work energy theorem to be valid, the kinetic energy has to be measured with respect to an inertial frame, and the displacement and the work done which you calculate also have to be measured with respect to the same inertial frame of reference. Otherwise, the theorem will not be valid, because F is equal to ma is valid only in an inertial frame of reference. Now, the advantage of this work kinetic energy formulation is that in a lot of problems there are forces which act on a particle, but do no work. Now, how will this be possible? Suppose if a particle is moving along the x direction, and if we have a force F1 which is acting in the y direction. Now, the work done by F1 will be equal to F1 vector dotted with dr integral of this with respect to r, and because dr is in the I direction, F1 is in the j direction, F dot dr will be equal to 0, and that is what we say, that certain forces do not do any work, and therefore, when we use the work energy theorem, such forces will not be accounted for, and therefore, they will, if they are unknown forces, then we do not have to bother about them. Now, some examples of forces which do not do work, well, we have seen typically when we talk of normal reaction, we have a block which is sliding up a plane or sliding down a plane. Then on this block, when we draw the free body diagram, the normal reaction acts perpendicular to the surface, and this is the displacement direction, and because n, so if the displacement direction, let us call it as r, because n, the normal reaction is perpendicular to r, therefore, this will not do any work. So, this may often happen. Then a second case which we see is, if a particle moves on a circular path. If it is moving on a circular path, and let us say there is a string which is holding this particle, we are slinging a stone tied by a string. So, now if there is a tension which is acting on the particle, this string force or the tension which we say, and the particle is moving in a direction which is perpendicular to the string force. So, here in case of circular motion, work done by T or the string force is equal to 0. And this could also be a case that there is a circular path on which a particle is moving. In that case, the normal reaction, once again which is acting from the ground, will be in a direction which will be perpendicular to the path. So, that will also not do any work. So, when we apply these the work energy theorem, we will see this happen. Let us look at some simple cases. The first case we will look at is a ball being thrown in air. So, we are on the ground, we have a ball in our hand, we throw it in air. So, we give it a speed v, I take a particle with a speed v, I throw it up in the air, and it is in free motion, the particle moves up. As it moves up, so we throw the ball up in air from ground with a speed v. Now, as the ball moves up, gravity starts acting down, gravity is acting in the downward direction. So, the speed starts to reduce, this is a retarding force. Eventually, a point comes where the speed of the ball becomes equal to 0, and at that point gravity is continuously acting down. So, then it starts to come down and it comes back to the ground. And if there is no air friction, then when the ball, as we have seen, when it comes down, it will have a speed v again. Now, if we look at it in terms of energy and work, then what we have is, at ground, at this speed, at ground when the ball is just left, the kinetic energy is equal to half mv square, and as the ball moves up, due to gravity, the speed v comes down, which means kinetic energy comes down, and at the top position, this is the highest position the ball will take, the velocity becomes equal to 0, which means the kinetic energy has become 0. Now, gravity increases the speed, and so v increases, or as the ball comes down. By v I mean the speed. So, it increases as the ball comes down. So, kinetic energy once again increases, and as the ball comes to the ground level, the kinetic energy restores its initial value. Now, what is happening is, gravity is doing work on the ball throughout. Now, in the upward motion, the gravity force acts down, the displacement is upwards. So, therefore, the work done by gravity is negative, and that is why we have change in kinetic energy is equal to work done. So, if work done by gravity is negative, then the kinetic energy reduces, and this happens till the ball reaches the top. At the top position, kinetic energy at the top position becomes 0. Now, as the ball comes down in the downward motion, gravity is acting down and the displacement vector is also down. So, therefore, now the work done is positive, and change in kinetic energy, which is equal to work done, is also positive. That means the kinetic energy starts to increase. Now, what it gives us a feeling that is the work done by gravity, can we look at this as, in some sense, as a stored energy? That is, as the ball moves up, there is some form of energy which is related to the position of the ball vis-a-vis the vertical position, which increases, and as the ball comes down, this energy decreases. So, that there is a kinetic energy and there is an energy because of gravity, and sum of these two may be constant. So, this could be a way of looking at how the work done by gravity takes place. We will formalize this, but before that let us try to also look at another example where a similar thing happens, where an external force acts like some sort of stored energy. Let us now look at a second case of a block sliding on a frictionless surface and encountering a spring. So, we have a spring which is there and a block of mass m moving with the velocity v is travelling in this direction and it moves and it touches the spring. So, now when the block touches the spring, the block is moving forward. So, this compresses the spring. So, what happens is once the block is in touch with spring, it continues to move forward, but the spring applies an opposite force on the block. So, the speed of the block comes down, V reduces because of the spring force. So, once the block touches the spring applies a force and we know the spring force is given by k times x. Now, what will happen is because this velocity of the block decreases, it touches the spring keeps on getting compressed. Eventually, a time will come when the block will stop and then the spring is applying a force in the opposite direction. So, because of which the block will move now in the opposite direction and so when the block stops, its kinetic energy becomes equal to 0 and then when the spring applies the opposite motion, the block moves again. We could think of this spring force, can it be treated as some sort of an energy, say we will call it as symbol V. Now, let us look at a third example where the work done by the force. So, now in the second case also the work done by spring, we are treating this, can this be treated as a form of energy. Now, let us look at a case, third case, case 3, where we have again a block of mass m, but now it slides on a surface with friction. So, it means let us say some force has been applied to the block, because of which at time 0 it has a velocity v 0. Now, at that time no external force is being applied to the block, it has already been removed. Because of the movement of because of the application of some force, the block is now at this stage it is moving with a velocity v 0. Now, what will happen is if this force, if the ground is not frictionless, there is a friction force, then as the block moves, if you draw the free body diagram of the block, its weight acts downwards, the normal reaction will act upwards and what we have is force of friction tries to stop the block and because of this force of friction the velocity v 0 will start going down and eventually a stage will come when the block will stop, let us say after moving a distance d and it comes to rest. Now, we have in this case, if you look at it, work which has been done by any external force on the block has been done by friction. And what has happened because of work done due to friction? The kinetic energy of the block from its state of half mv0 square has become equal to 0. So, that means the kinetic energy has become equal to 0, but because of the work done by friction. But now, if we want to bring the block back to its original state, then we have to apply, that means if the block is stopped here, if I want to bring it back to its initial state, I have to put some other force, and this force has to be applied again. Now, you see the difference in the previous two cases and this one. In the previous case, when the ball reached at the top of its path and when its velocity or kinetic energy was 0, then because of the gravity force it again acquired a speed and it came down to the ground. And similarly, when we had this block tied to the spring, when the spring was compressed and the kinetic energy became 0, then the spring energy in some sense pushed the block back, and so that it came back to this state and then it went further. So, in both these cases, the two cases earlier, the work done by spring and the work done by gravity in some sense stored some energy, whereas in the third case where we have the friction force which is acting, the work done by friction, we cannot get it back. What happens to this? This is some sort of an energy which gets dissipated. So, based on this we can say that there are certain type of forces where or whose work can be stored as energy, and this energy due to these forces we will refer to this as potential energy. The symbol which we will use for potential energy will be V. Now, if we look at the work energy theorem, the work energy theorem tells us work done by forces is equal to delta K. Now, let us say on the system only those forces are acting. Let us look at simple case, only gravity is acting or only spring force is acting. Then in that case, if we have the work done by those forces can be specified as a potential energy, then what we can say is change in kinetic energy plus change in potential energy is equal to 0. And if we compare these two expressions, then what we get is work done by those special forces or those external forces, this can be written as minus the change in potential energy. So, if we have a force whose work can be stored as energy, then work done by force would be written as minus the change in potential energy, and this we can write it as minus delta V. So, what we say is if the system changes from configuration 1 to configuration 2 because of a force being applied, then the change in potential energy will be given by minus the work done by that force. But as we have seen, not each force can be written in the form of change in potential energy. So, first let us see if we write the expression for potential energy V is equal to change in potential energy is equal to minus the work done by that forces. So, that will become equal to minus of f dx, where f is the force and this integral will go from xi to xf. xi is state 1, xf is state 2. So, change in potential energy will be given by minus of f dx, and this will be from state x1 to state x2 or xi to state xf. Now, if the initial state xi or xf is the reference state, and if we use the symbol 0 for the reference state, then what we can say is potential energy at any x minus the potential energy at x0, this will be equal to minus the integral f x dx with x going from x0 to x. So, this is how we can define the change in potential energy with respect to a reference state. Now, one thing which we realize is when we use the potential energy formulation, it is the change in potential energy which figures in our equation. Change in potential energy, which means that because we are talking of the change in potential energy, the reference value of V of x0 is not important. We can assign it any arbitrary value we want, and often what we will do is we will assign, if we choose x0 as 0, then V of x0 is often taken as 0, and this will become clear when once we do a couple of examples. Now, potential energy, this concept of potential energy is applicable only to those forces whose work is stored as energy. This is how we will qualitatively look at it right now. When we quantitatively look at it in more details mathematically, maybe when we do higher courses, then we will have other ways of quantifying this. But qualitatively we will say potential energy applicable to only those forces where work can be stored as energy, and these forces whose work can be treated as some form of energy, we call them as conservative forces. And what we have is, if we look at this expression, V of x minus V of x0 is equal to minus the integral from x0 to x f dx. This is how we define the potential energy of those forces. F is the force, we integrate that with respect to x, and that is how we get the potential energy. We get another relation from here. If we differentiate this expression, then what we get is dV by dx is equal to minus f of x. So, this is in some sense an inverse relation. If we know f of x, this is equal to dV by dx. The integral form of integral of f gives us the potential energy. If we know the expression for potential energy and we differentiate that, we will get the expression for minus of f. Now, some points which we realize about potential energy: when we talk of work done by a conservative force, and so far at least we are presuming there are two conservative forces, which at least the notion we have, gravity and the spring force. Now, we will show when they are conservative. The spring force in particular is conservative only when we talk of linear springs. But work done by a conservative force, this depends only on the initial and the final position, and not on the path taken. And that is why we can define this work done as some sort of integral, of the integral of that force work done, we quantify it as some sort of a scalar which we call the potential energy. So, the work done will not depend on the path. For example, if we have a body which is moved up from position 1 to position 2, we move it up an incline, and so here the work done by gravity will be just a function of positions 1 and 2 and not the path. And what we mean is, even if the particle moves along a path A or path B or path C, or let us say it takes, first it travels horizontally, then it travels vertically up, any path which the particle takes, the work done by a conservative force will be the same irrespective of the path which the particle takes. And in case if the work done depends on the path, then the force is not conservative and we cannot define a potential energy. So, it has to be path independent. Secondly, if we look at the dimension of potential energy, dimension of V, this is the same as that of work done or energy, which is m times L2 t to the power of minus 2. The third thing, which is a corollary of the first one which we looked at, is if suppose we have a body 1, it travels along some path and comes back to its original position. So, a body travels a path and comes back to its original position. Now, if a conservative force acts on the body during this position, what will be the work done by the conservative force? The work done by the conservative force as the body starts from position A and comes back to the same position, which means it has followed a closed loop. Mind you, the loop may not be circular, it can be any arbitrary loop. So, the body starts from here, comes back after moving, then the work done by a conservative force, if it is acting all along this interval when the body is moving, the work done by conservative force will be equal to 0. Why? Because the work done can be written as change in potential energy, and potential energy is only a function of this position. So, Vi minus Vf or Vf minus Vi will be equal to potential energy at the final point minus potential energy at the initial point will be equal to 0, as position I is the same as position F. So, a work done by a conservative force when the body moves in a closed loop is equal to 0. So, in particular, if we have two positions A and B and the particle moves under the influence of a conservative force from A to B, and comes back from B to A, then the work done by the conservative force will be equal to 0. So, in this case what we can do is, if work done from A to B plus the work done from B to A when the particle comes back, this is equal to 0 if F is conservative. And what this tells you is, work done from A to B is equal to minus the work done from B to A if this is along for a conservative force. Now let us look at the potential energy and some conservative forces. These are the typical conservative forces which will come in our problems when we solve, which are common to day life. And the first conservative force which we have seen very clearly is gravity due to Earth's surface when a body is moving near the surface. Why do we put this position? Because when a body is near the Earth's surface, so if this is Earth and a ball, let us say, is thrown up, it is nearby, then gravity force pulls it down, and this gravity is constant if the distance from the surface of the Earth is not too much. We know otherwise we have Newton's universal gravitational law, which tells us that gravity is a function of distance. But if we are near the surface of the Earth, we can assume that gravity is constant, and this gravity is essentially, it's a conservative force. And the potential energy due to gravity can be written as mgh, where h is positive when we are going upwards. Upwards means opposite to gravity. So, if we are, let us say, this position, let us say it is on ground, we call this as 0 position. If we are at a height h, then at this position the potential energy we can call it as mgh. Basically the difference of potential energy, we should put it as Vb minus Va is equal to mgh, where gravity is acting downwards. H is the height, distance, the vertical distance between point A and point B. So, this is how we calculate the potential energy due to gravity force on Earth. Now, what can be done is, we can choose the reference level as 0 at any point. That means, if at the surface of the Earth we say potential energy is 0. So, we can choose Va is equal to 0, then we get Vb is equal to mgh. In another problem, we can choose Vb as 0. If we choose Vb as 0, then Va will be equal to minus mgh. And you will see it will not make a difference, because when we solve problems we talk of change in potential energy. So, if we are talking of Vb minus Va will be equal to 0 minus mgh, which is plus mgh, and even when we take potential energy at A as 0, then we get Vb minus Va is equal to mgh. So, therefore, this is, so it is up to us to choose the reference level here. And if we move down, let us say, if we are moving down, if this is position and if this is H1, this is A, this is B, then we have, we will look at, if Va is equal to 0, then Vb will be minus mg times H1. And if suppose the 2 points A and B are like this, and this is the direction of gravity, then what we have to do is, when we calculate Vb is equal to Va plus mg times delta, where delta is the vertical distance between B and A. And you see the simplification which comes because of this formulation is that what we are bothered about is only the change in potential energy to calculate the work done by gravity. See, our original equation of integrated form of Newton's law is W is equal to minus K. Now, if in a problem there is only gravity acting, then what we have shown is the work done by gravity can be written as minus the change in potential energy, and to calculate V due to gravity, all we need is the vertical height of the body. So, whether the body is moving along a curved path, inclined path, it does not matter. At the position of interest, we need to find the vertical height with respect to some reference position. So, the calculation of work done becomes quite easy when a conservative force acts, because we use, instead of W, we use the minus the change in potential energy, and we do not need to then bother about the path the body actually takes when it moves from position 1 to position 2. The second case of energy which we have, so the second case of conservative force is when we have a spring which acts or which applies a force which is given by Hooke's law, where the force spring is equal to minus kx. If the spring is such that the force is proportional to the displacement of the spring, then such a spring force is conservative, and we can define a V associated with this spring force. And how do we do that? Suppose if, let me just draw it again, we have a block connected to a spring, and let us assume that this surface is frictionless. Then what we do is we count, start with x is equal to 0 is the unstretched position of the spring. Now, if the spring is compressed by distance x, then the work done by the spring force, this will be equal to integral from 0 to the current position, let us call it as xm, it has been displaced up to this position, this will be equal to integral fs dx. And this force due to spring, we have seen this is equal to minus the kx dx, x going from 0 to xm. So, this becomes equal to minus k times xm square by 2 minus 0. So, therefore, the work done by spring is equal to minus k times xm square by 2. And work done by spring is equal to minus the change in potential energy. So, the potential energy, change in potential energy can be written as k times xm square by 2. So, what we have is, if a spring is compressed by an amount delta, the potential energy for the spring can be written as half k delta square. And what we will realize is, even if the spring is extended by an amount delta, once again the potential energy of the spring will become equal to half k delta square. And for that all we have is, this will again be, because spring force is acting in the opposite direction, this same thing will happen minus k x m square by 2. So, therefore, the potential energy, so what we can say is, if we have a spring, we can call it as a linear spring. By linear spring we mean force due to the spring is equal to minus kx, then the potential energy corresponding to this spring, we can write it as half k delta square, where delta is the displacement of the spring with respect to its unstretched length. So, now we have seen two forces which have, for which we can write the potential energy, force due to gravity and the force due to a linear spring. There is a third type of force for which potential energy can be defined, and this would be potential energy due to force of gravity between two bodies, and this we are talking of the universal law of gravitation, where we will have this force if we have a body m1, another m2, and if this distance between these is r, then we have the gravitational force is equal to minus g m1 m2 upon r square. In the direction, if we call this as the r direction, then force on body 1 will be minus g m1 m2 by r square in the opposite direction. So, m2 will exert a force on m1, it will pull. So, force on m1 will be in this direction, force on m2 will be towards m1, and this is given as g m1 m2 upon r square. So, because if we talk of force on body 1, then m2 is here. So, r direction will be in direction from m1 to m2, and the gravitational force will be on m1 will be towards m2. So, therefore, we have these the minus sign comes. So, we have the universal law of gravitation which is there, but this we will see once we complete this. There is a separate chapter on universal law of gravitation. So, now we can generalize this law of, we have looked at this the work energy theorem. What we have shown is that we have change in kinetic energy is equal to work done. Now, work done will be due to several forces. In general, when a body is moving, many forces act on it. Now, some of these forces we can divide them. Some of these forces will be conservative forces, others will be non-conservative. So, what we can say is change in kinetic energy will be work done by conservative forces plus work done by non-conservative forces. Now, the work done by conservative forces, we can write it as change in potential energy corresponding to each of these forces. So, this term can be taken on the other side, then what we get is delta k plus delta v will be equal to work done by non-conservative forces. Now, if there are no non-conservative forces, and this happened when we took the first two examples of a block sliding on a frictionless ground and hitting a spring, or a ball being thrown up into air. Then what we have is, if there are no non-conservative forces, then the work theorem becomes change in kinetic energy plus change in potential energy is equal to 0. and this is what we call as the principle of conservation of mechanical energy. But for this principle to be valid, keep in mind the non-conservative forces which are acting on the body do not do any work, and the work done by conservative forces is accounted for in the change of potential energy. So, therefore, only in a system where non-conservative forces are not acting or they do not do any work, change in kinetic energy plus change in potential energy is equal to 0. Otherwise, this change is equal to work done by non-conservative forces. Now, we can slightly generalize this, and if we say that the work done by non-conservative forces is equal to minus the change in internal energy, and this would mean that there is some sort of dissipation which has taken place. So, this goes to adding the temperature of the body or change in internal energy which gets dissipated as heat or some other form, and then what we can get is change in kinetic energy plus change in potential energy due to conservative forces plus the change in internal energy is equal to 0. And this then can be seen as a generalized form of law of conservation of energy. And in the change in other forms of energy, there could be energy could change in other forms, not just mechanical energy, there could be electrical, chemical or nuclear, then all these would also be added like delta U here. And this would then become the generalized form of conservation of energy. So, today we have seen the concept of potential energy and the work energy theorem, and in the next class we will look at one or two simple problems where we will see how work energy theorem helps us to solve things in an easy way, and then we will look at the principle of conservation of linear momentum, which again is an integrated form of Newton's second law. Thank you.